Panic. 3, 2, 1, go. Então, já não vou falar em espanhol. Poquito difícil para mí. And so it's going to be in English. I hope everybody is going to be comfortable with my very strong French accent when I speak English, but it's not that strong, it could be worse. So hopefully it's going to be okay. So I've been introduced already. So my name is Eric. I'm a professor at the University of Campinas in Brazil. I teach robotics for postgraduation and electrical and nuclear engineering for undergrad students. And also I have been involved with the development of this simulation software called VREP. This software from Popular Robotics, a Swiss company. This is my email address here. If you wish to contact me afterwards for more questions, I will be happy to help you out. So I guess that everybody already installed the VREP on their machines. And we are going to go first through a small talk about VREP, what it can do, how it could be useful for you as an engineer in production, industrial robotics engineers, for instance. You will be able to use VREP. And then we will have a small tutorial about applying what Andres presented. That will be developing this robot, which is a differential drive, very simple differential drive robot that we are going to build in VREP and then simulate and then put some controllers in there, a little bit of autonomy in there, and that would be it. So this kind of platform would be useful in an industrial context because flat ground and you can have this kind of mobile platform. You can put a robot over it and a manipulator over it and do some kind of stuff. So let's go. Let's start. So what is VREP exactly? VREP is a simulation software, but I don't like to call it like this because it's doing much more than simulation. It's I like to call that robotic simulation framework, because if I said simulation software, it's like only to develop some simulation, but it's not only that. I'm going to show you that you can link the software with a lot of hardware, either like for input purposes, like to control. You have a hardware like a joystick or like a novel kind of interactive device with the machine. You can make the interaction with VREP, or in the output you can plug a real robot. So that might be very interesting to have some money in terms of Industry 4.0 as a new team. That is, you can use VREP as some kind of testing device to test your production and also to test your communication, the communication between your application and the industrial plant virtually, not using the real one, using a virtual model of it. And also you can use that as a monitoring device, etc., etc. So VREP can do all of these things. So this is actually a very nice video that I'm going to show you that shows about a lot of possibilities that VREP is offering. So in this scene you have like 4 robots, different kind of robot. You have the very standard manipulator, industrial manipulator. You have a little bit less standard, but like coming really much into the industry, parallel robots. Also, very new kind of industry is this kind of robot, mobile manipulator. So this is a KUKA U-bot robot, and also some kind of different than industrial robot, this kind of hexapod walking, which is able to walk. And they are all playing together against this robot, 2 different games. This U-bot will be working a chess game with this robot. This robot will be challenged at a tic-tac-toe game by this one and this one, 2 different robots. You can see that there is a camera here, here, and here. I don't know if you see properly. And this camera is actually used process images of the game in order to have some intelligence, artificial intelligence, sending commands and taking decision of what the robot should play. So here, this is the chess, this is one of the tic-tac-toe, and this is the other one. Also, you can see that there are like different kind of tools. Like, well, you will see later in the video. Okay, I'll show you. It's very interesting. Okay, so in this video we see first the parallel robot plays chess. It's grabbing some pieces based on what the camera sensor is showing, and the algorithm is taking extracting some blobs and playing around. Then he's playing some tic-tac-toe with changing tool, taking some drilling tool and making his move with this tic-tac-toe, while this robot is actually drawing on the ground some tic-tac-toe his move. So you can see, the parallel robot is actually gripping the tools, while the industrial robot is having a suction cup. So it shows like very different kind of concept. You have like motion planning, fast planning, action planning, like decision making with game, and filtering. You can be filtering some information with the sensor. You have like some all of these features are integrated into the app, and you can use them to do some fast prototyping or testing, monitoring. You can see that the camera is moving like in a cinematographic way. Not anymore, but it's not moving. It's like traveling and stuff. So all of this can be done within VREP, programming small scripts and building a scene. So I'm gonna keep on going. But as I was mentioning, VREP is not enough. It's not only simulation software. You can actually connect it with the external world. I was mentioning the devices like input devices and output device. So as an output device of VREP, I have a computer, a robot that is actually controlled by the simulation of VREP. So the simulation is actually sending the robot control based on the input of this remote. You probably know what the remote is. It's like a very nice device that handles motion. So with motion, I can control the simulation of the robot that controls the real robot. And the real robot is sending back its position to the simulation, and I have a monitoring device. Okay. You can do other kind of things, like this is also a PlayStation Move device or input device, where there is a camera detecting the position of this sphere, and there is a sensor here for the orientation. And I can control the end effector of this manipulator, like the invert kinematics. I'm pretty sure you're familiarized with that. Is handled by the sensor. Yes.
Just control with the hand.
Yes, with the hand you the movement of the hand for this here. There's a camera that is somewhere around here. This is the camera. It is connected to the computer, and I'm detecting the position, spatial position of the, making some filtering to detect the position of the sphere.
Cameras and sensors.
The camera is the camera is it's a webcam. It's a webcam plugged to the computer.
It's just this webcam.
So
it's just a webcam.
Yeah, just a webcam, making some detecting the lights. Taking an image, detecting the color, filtering the image, and detecting where detecting the blue part because it's blue, detecting the center, and it knows we know the size of the ball. So if the image has a big ball, it means that it's close, and if it's a small ball, it means that it's far. So you can do the mathematics to detect in 3D where is the ball in 3D. In the environment. Then you can map that to the simulation, to the end effector, and you control and you say, okay, the position in space of my remote PlayStation Move is mapped to the position in space to the end effector. So I can drag the end position wherever I want, and you will have to compute the inverse kinematics of the manipulator. But this is handled as we can see by VREP if you want. Another example is this one. So this is the laboratory my laboratory in Campinas. We have the robot, this robot with the computer running the simulation, and inside the simulation I have a feedback of the real feedback of the video. As you can see, I have a virtual world that's the representation of the real world. They are synchronized, and when I click somewhere, I'm going to be clicking here in this video. I will be putting in the simulation a target that the robot will follow, will reach. So there is a path planning and then a path following algorithm doing that inside the simulation and sending the command to the real robot. So here, for instance, now I'm going to click here, like on this mark on the ground, which is there, here, and the robot is going there. So you can do this integration of real world, external, and virtual world to do some nice things. This is the view from the simulation. So same, I'm going to click here, okay, getting there and clicking here. And this is like, this implementation is a few hours of work. It's really fast. It's thanks to VREP functionalities. Another example of input, so I have in my hand an augmented reality tag, which is a mark, like a square with some detail in there, that is recognized by the camera, and the algorithm is filtering the image in order to, it knows the patterns that it needs to see, so you can see by the deformation of it, you can extract the position and orientation in space of the tag in the camera frame. So same principle, I'm getting a position and orientation in space, so I can map that to the target of a manipulator, and you can have some tracking. So this is useful if you want to put the tag close to a door knob, so that you will know where the door knob is, and the manipulator will be able to take it and open the door eventually. So this is the tracking. The tracking, and this video is bad, but this is the only one I have that shows that actually I'm controlling this virtual manipulator, but sending to the real one the commands. So you can see that the manipulator is the real manipulator is following the angle I want it to. Okay. So robots. What kind of robots? Mobile robot. I will be focusing on mobile robots on this talk, but you see also some few production line robots, and I will talk about it also. So you can, for the iris competition, for instance, that Andres was showing, he was showing like the design of the two-wheel robots, but you could go for one-leg robot if you want. So basically it's a jumping robot. It needs to jump in order to keep the balance. So you can study the dynamic in VREP and then implement your design in a real world. Okay? It's better that the simulation falls, the robot simulated is falling than the real one. Two-legs robot, like humanoid robot. Like this robot you have like plenty in the university, like 24 or 25 robot like that. So you're going to be able to use it. And you can see that the real robot is behaving like the simulation, or the simulation is behaving like the real robot. You can modelize, this is VREP, you can modelize a full environment, and that's it. It could be like a two-leg robot, like it's a little bit scary, but it's a nice one. Also for the Alice competition, could be an advantage to try to eat the other contest, the other people, the other robots. But two legs, it's a little bit slow, so it's good for rough terrain, but spending a lot of energy and going very slow. Could be four legs, it's more stable. Like this is the famous Ivo robot, which the video is not working, I don't know why. Again, okay, simulation of it. It's strange. You can go also for more legs. Exactly. And this is creepy, but it's very nice for rough terrain. You can simulate this kind of robot. Also, you can be creative and using a one-wheel robot, but I don't suggest to use that anywhere actually. And the video is not working. That's a bummer. Okay. The video is not working, but it was one-wheel robot. You don't want to use that. I need to find out. Four-wheel robots are very good for rough terrain, especially with this configuration. This is not a steering model. This is like 4 wheels, like fixed. And you by making some combination of wheel rotations, you are able to modelize. You can modelize this robot like it's a skid steering robot, but it's kind of modelized like the robot Andres presented, the differential drive. This is another kind of robot that you have never ever seen. It's 4-wheel robot called a car. So it's Ackermann device. Ackermann is Ackermann steering. You have 4 wheels and 2 of them are. You can switch the heading and you can have some. Yeah, that's bad to do in real life because it's running away. So that's really bad. Stop at least, no? I know it's a robot, but still. And this is a track vehicle. This is actually Queens, the robot Andres introduced briefly. The first Japanese robot. It was a little bit French because I wasn't part of the team, but they would not say that. It's a Japanese robot who is in Fukushima. So you see that there is so it's a track vehicle with flippers, and when you make the design of your robot, you could use the simulation to be sure that what you want to design is going to work. So in this simulation, I can show that the algorithm was tested, like based on some software, based on the same hardware than we use the same sensor and the same algorithm, and we were able to test the stairs climbing algorithm before. Actually, it was not true, but we didn't do that. We would have been able to test it in the simulation before actually making the robot. So how does that work? It works like I have one sensor that detects the distance and one sensor that gives me the pose of the robot and some encoder to know where the flipper are. And based on where the robot, how the robot is oriented, and depending on the distance that is detecting, if it is the floor or if it is a hole, I will update the flipper to maximize the friction for the mobility of the robot. So why are you doing that? Well, those are flippers, so you map that to buttons, so you have like plenty of buttons. It's a Japanese robot and they are very good with video games, so they can handle like plenty of buttons to move like the flipper and the stuff at the same time. But anyway, you need a good training for that. So with this implementation, you just give the direction of the robot with a joystick, and the flipper will move accordingly, autonomously, in order to let you overcome some obstacles. So it is a very, very good robot for accidented terrain, like very rough terrain. So good that it's the only one robot in the world that was able to go up to the 3rd floor of the reactor number 1 of Fukushima, better than the American one. Just saying. The American one, they were the first to get inside because it was ready for radiation. The robot was to war and went to war, but they were not able to go to the 3rd floor. So we took a little time to modify the robot in order for it to sustain the radiations. But once it was done, it was able to get inside and went up to the 3rd floor and get some data, some places where if a human goes 10 minutes and he's dead. So that's a good thing that we have robots. And you can be creative for artist competition, like for instance, not only that this is working, damn it, it's very strange. Anyway, I have a simulation here of this robot. You have to trust me. This robot is nice because you see it's a walking robot, but then you switch its legs and it becomes like a skater robot, which is very, very cool. See, you can They will navigate like that. This is a Japanese robot from a laboratory called the Hirose Lab. And this is a Boston Dynamic robot, which is a American company, which is pretty nice. It could do a lot of things. I wanted to show you the simulation, but for some reason, I don't know why it's not working. Okay. So VREP, let's go. So those were some examples of robots that you can do. I'm going, actually I can show you some, I want to show you some more things. More industrial robots. Seems, let's see. Industrial robots. Like, that would be nice to show you. So this is some stuff that you are actually willing to do, I guess, as industry engineers. Like doing this kind of thing is not trivial. See, it's picking up something, making some motion, finding another space, approaching, picking up, changing. In VREP, you can actually do stuff like modelizing some manufacture plant. Like, no, it's not the one. Where is it? Equipment. Conveyors. You have like, you can put some conveyors on the first plate. It's going to be like this. You can put some industrial robot. Robot. It's going to put like something like this. Too far. See, something like this. You can put also some people, simulate some people around. Some people pretending to be working, like this one. Whoa. It's working fast, working fast. Yeah, actually, let me put it somewhere else here. Yeah. And we go in real time. It's more like this. Or some people moving around. You can. Yeah, so this might be interesting for you in order to test. So you mount your manufacturing in VREP, and then you put some people. You can script the motion of some object, like people object. Like this guy is an object in the simulated world, and simulate a motion or something like it, and simulate a behavior that is not recommended in an industry or in a manufacturing, and to test your securities, or something like this. Or for Industry 4.0, we have a switching of the paradigm of having robots like confined into a space that nobody can enter. If you, the security was like that. You have a very dangerous manipulator that doesn't know about his environment. He will move and do his stuff. So if someone is on his way, he will be punched, crushed, killed, maybe. So to avoid the accident in the manufactory, well, the traditional technique was to close the environment so that the workspace of the robot is not accessible while the robot is moving. Now we are not like that. We have like some cognitive smart manufacturing, where the robots are actually starting to be collaborating with humans. So this means that we need to have algorithm and sensor and hardware that are able to be safe for humans. Like if the human is on the way, it needs to be detecting him, or doing some stuff that are not very dangerous for him. And this can be implemented, tested, and you don't want to implement the thing and ask your coworker, just go over there, let's see if it's working or not, my security algorithm for the robot. So that you don't want to do that, you want to test that manually. So you can modelize your plan with VREP, for instance, and then have a virtual coworker to do the task and trying out if you're going to be safe or not. So this is one thing that you can do with VREP. And how to do this kind of thing then? Now, how to do that? So VREP is based on 3 central elements. So you have scene objects, calculation modules, and control mechanism. So the first one is scene objects. Scene objects are everything that you have in VREP. Like, there are like building blocks, like Lego blocks that you can use, combine in order to modelize the environment, make your robot, make your sensor, etc., etc. So those are the different kind of objects you have in scene object you have in VREP. Very important ones are shape, obviously, to make some, to have something to show in the simulation to modelize the robot or the environment or the sensors. Joints. These objects are motors or simple joints, like passive joints, like hinges, or they can be some motor, linear motor, or spherical motor. You see there are several. Cameras. It's another type of object that is required to show the point of view of someone, for instance. Lights, you need some, you don't see anything. Dummies, very useful to be able to set a reference frame. Mirror, not very useful. Graph, if you can make some graph to display in 2D, in 3D, also directly in the scene, to analyze the motion of the robot, for instance. Paths and trajectories. Paths and trajectory, this object is like that you will compute a path for the robot to reach a certain position or orientation or both, and you will be able to follow it. It's another object. This is to simulate the drilling of an object. This is a vision sensor, is a type of sensor where you are like the one we have seen for the chess playing and the tic-tac-toe. Torque sensor, force torque sensor, so you know what it is. And proximity sensor are a kind of sensor that detects distance, basically. And all of those sensors, they can be modelized in a way that you take the real sensor, look at the specification, and reproduce the same thing with the sensor. For instance, if you have a sonar, you know what a sonar is? We're going to use one. Sonar is basically a device, a sensor that is projecting a sound, and when the sound is bumping to an obstacle, it's coming back. You measure the time that you send and the time that you receive. You divide by 2 because it's like going and coming forward, backward. Divided by the speed of sound, you have the distance. That's the sonar. And the sonar works like this. You have it's kind of a cone of information that you have. It's exactly like that. It's a cone that after a while you're not detecting anymore, so you can define this, the angle of the cone, the size of the cone also, and put some noise on it if you want. And that's a sonar. But if you have a laser, you have laser also to if you want to measure distances. Based on about the same it's about the same principle to detect the distance. But the laser is not a cone; it's more than a ray. It's more like a ray. So you can change the form of this sensor and adjust it based on the real one in order to have a simulation that is very very realistic. So proximity sensor already told you. Graphic is like this kind of things. Those are screenshots from the earth actually. This is a funny one. The robot cat is looking at the mouse. So the vision sensor allows you to make some filtering on it. Like you will be detecting the shape and where the center of the image is. The center of the shape is, and have an estimative of the size. For instance, so that could be in a manufacturing plan. You can have this kind of behavior. So you have a robot that is walking. It's got a sensor here, a vision sensor that is filtering this image and detecting the color of this other robot. And the filtering is providing you information about the position and localization of the robot, and also the depth, how close or far away the robot is with this size of the line. If the line is big, well, you're close, and if it's small, well, you're far. So the robot is following it up to a certain distance. This white robot is following the red one up to a distance. You see it's reducing its speed. And this robot is having another behavior, basically going straight until this straight shape proximity sensor is detecting an obstacle, and then it will be going in another direction. And here you have the graph that you can export afterward for analysis and stuff. Okay? Pass and milling. Do I have internet here? No. It's okay. I can see this. Camera, light, mirror, I'm going to go a little bit faster because of the time frame. So shapes, they can be shapes that you import from your favorite CAD model. You want to design a robot, we're going to design one, but a very simple one. But what you can do is modelize your robot with your favorite SolidWorks or AutoCAD or whatever CAD model, CAD software you like. Make the shape of it, and you can export it to direct. And from there you can modelize all the dynamical behavior, etc., etc. So there is a big, nice tutorial to how to do that in the VREP help. I will show you how to access this help. Joints, I told you, those are motors or passive joints that can be revolute, so motors. Prismatic cylinders, very useful for the design effort if you want to modelize some production line. Screw type and spherical type. Force lock sensor to measure force and torque, and you can set. This is actually a nice feature. You can set the breakpoint, meaning like I have this robotic arm. No, I'm not a robot, but just as an example. I have this robotic arm. I'm fixing it here with my body, and I put the force torque sensor here, so I can measure the force and the torque of that is applied to my arm. Okay, no worries. Now, if the torque or the force is high enough, over a threshold that I can parameterize, I can break this thing, so my arm will fall. So that's, you could simulate some something like for the R-list project, Andres was saying that there is a part where the robot is falling and could break, so you could actually test this kind of behavior within the simulation. And dummies are basically auxiliary reference frame. So those were the objects. Another central element of VREP is the calculation module. Calculation module are algorithms that are inside VREP that are helping you with the fast prototyping. And you have several kinds of modules that we're going to talk about all of them. Like for instance, you have the collision detection module, physics, dynamic engine, physics and dynamic engine module, the path motion planning, forward and inverse kinematics, and minimum calculation distance. Forward and inverse kinematic. I'm pretty sure you know what this is about. Everybody had some manipulator. Have you ever had classes about manipulation? No? Not really? Not yet? Okay, so forward kinematics is when you have a manipulator, you have a set of joints, and in an industrial context, not only, but you often want to use the manipulator to pick up some parts, right? So forward kinematics is if I put this angle, and this angle to the robot, what will be where will be in the space will be my manipulator, my tool. Where will it be? So this is forward kinematics. This is not complicated not so complicated to calculate. There's a lot of matrix, but matrix manipulation, but multiplication. But it's not too complicated. The inverse problem is a problem. It's more complicated. If you want to put the robot into that and that position and that orientation to be able to pick up something, what are the angle I need to send to the real robot? This is the inverse problem. This is the inverse kinetics. And this is it could be very tricky. So depending on the complexity of the manipulator. So VREP is doing that for you if you want. This is very useful. And it's doing that for very complex robots, like with a lot of degree of freedom. Like this one. This is a very complex things. And you have another step that is the collision detection, which would be a tool that is pretty interesting. Like to test with your virtual coworker, to test your algorithm. Like you can detect when and if the robot hits the virtual coworker. You have also an algorithm that you can use that is the minimum distance calculation. So this is like to know what is the distance between two objects. So what is distance between two objects? It's mesh to mesh. For instance, the distance between me and you, for instance, what is it? How to measure it? So that would be maybe my knees up to your elbow. Like some point here from here. That would be the minimum distance. So VREP does have this kind of calculation algorithm implemented. So it's from the mesh of this model to the mesh of this model. Like the closest one will be detected very quickly. Motion and path planning. Motion and path planning is like you have it's another calculation module that you can use in order to define what would be the motion to do to reach a certain objective. I think I'm going to show you this demo that I really like. You can see where it's planning. Where is it? This one. So this is a box. You can see this is a box. Okay, closed box with transparent walls, faces. This is the object that you want to move to this position with the going through this hole. Okay, so let me modify. And the position also. Okay. So I put this is the target for this object to go. I want this object to move to this position and orientation through this hole. This is a pretty complex problem, I guess, calculation. So it's possible, and let's see if it does that. So it will compute for yourself automatically how to do this. So it's looking for it and hopefully finding a solution, unless there is no solution. Maybe there is no solution. Something went wrong. My computer. Okay. Computer. So there's no solution. Yeah, I must be. I think I'm having there must be some collision somewhere. Okay. So how am I touching something? Let me move it a little bit. I think there is no solution. That's why I'm not like this. Here I should go. Demonstration effect. So unable to sample any valid. Okay. Maybe the original. Maybe it's the starting point that is. Should be working. Find something. This, I don't know what is happening. Something is wrong with the. Well, okay, let's move on. I'll show later, I don't know. Maybe it's taking time to find a solution somehow, I don't know why. So, another module is the dynamic and physics module, calculation module. So those are actually required to compute the dynamic of the, if you want to have a dynamic simulation, you need to use this module. We have 4 different physics engines inside the array. Bullet and Open Dynamic Engine are like game-like engines, not very precise, so you have a realistic simulation. But if you are changing parameters for the simulation, some of them are not realistic ones. They are not physical values. So you have to do some tuning sometimes to make the simulation stable or something like this. This is because they are like fast algorithm but oriented for games, so you don't, and they are for free. This one is high fidelity dynamic engine, but it's not free. And recently we have this one, which is free and high fidelity. High fidelity means like every single values that you are putting inside the parameters for the dynamic engine has a real physical signification. So this is very, very useful. You can switch, you can select the one you want to use before running the simulation, which is very nice. And the last one of the central elements is the control mechanism. So now we have, with the scene object, we have modelized our environment, we have put some shapes to link together with some joints to make a robot, for instance, and something like this. And we are using some calculation module like the dynamic engine and these kind of things. Now what we need to do is to put some behavior to the robot. We want to simulate it. So this is the control mechanism element. So this is like several ways for you to say to the robot, okay, now I want this joint to go to that angle at that speed. You have these kind of things. That's the control mechanism. And we basically have six control mechanisms possible. So we're going to be working on this one, which is embedded script. It's scripts that you can put attached to any object inside the simulation that will be controlling any object of the simulation. Those are written in Lua language, which is very simple to understand programming language, scripting programming language. You can do some plugins. Plugins are some elements that you can add to VRL. For instance, I told you that you have like some vision sensors where you can filter the images of, you can get an image and filter it in order to extract whatever. And we have a list of those filter implemented, but sometimes the filter does not, the filtering you want to do does not exist. You can, you can have a quick. Yeah, I'm good with that. Don't worry. Don't worry for me. I mean, just I have to enter into the motion. So what was I saying? So yeah, so plugin you can add some more filtering if you want. You can program them in C++, or it could be like you have a robot. And you build a real robot, and the robot comes with an API. An API is some line of code to be able to program and interact with the robot. And you want to link that to VREP. You can use a plugin to do that. That's what I did when I showed you the video where I have the remote to control to interact. You remember? Yeah. So what I did is like, oh, I have a remote. That would be nice to use with VREP. But there's no way to connect it. So I looked in the internet for a free library someone developed already in C++, the code to access the remote, to read the remote. So I took this library, I put that into a plugin, and make some new functionalities with VREP so that I could access from VREP with a script, with an embedded script, I could access this the remote device, reading the orientation, reading the state of the motor, etc. Adam is another some other stuff on the class, and you can see that all of those style of those elements are localized into the same machine. They are like linked to VRF, like embedded script. They are inside the simulation. Plugins, they are loaded when you are running VRF. So this is in the same machine, but often you have one machine with VRF and your simulation, and you want to communicate with. And you have on the other hand you have your platform that you develop to control the real robot, for instance, and you're like, oh, that would be nice to be able to reuse all the code that I have already to control the real robot, but instead of controlling the real robot, controlling the simulation. So how to do that? I could use this which is called the Remote API. Remote API is a library that you can integrate into your own code. If you're coding in Java, in C++, in MATLAB, in Ruby, in Python, in Lua, we have several languages. And so I have this code that is controlling already my robots, but I can modify the code just integrating this Remote API client to control directly the simulation. How? Through the network. So we have a connection from here to here, like there is a network. TCP/IP communication. Custom solution is the same, and ROS, I don't know if you heard about ROS, is the robot operating system. This is something very popular now in the robotic community. Anyway, let's go. And embedded script to show that this control module is like what links everything. I'm going to show you that. So this is a laser rangefinder. Who does know what the laser rangefinder is? Nobody. Laser rangefinder is a sensor that is using a laser. Laser rangefinder to measure distance. So how does that work? You have a laser. I told you that already that with a laser you can measure a distance. So you have one laser that is measuring one distance. And then you put a mirror, a rotating mirror. The rotating mirror will diffract the laser to different orientation. Like this. So with one laser and one rotating mirror, you can have plenty of measurements in the plane. So I'm showing the laser here, at you, sorry for your eye, here. It's eyesight, don't worry, especially in the simulation. And I'm measuring distances on the plane. So this is it's pretty expensive sensor, but it's very useful for a robot. You put that on a mobile robot, and it will be able to detect the obstacle in front of it. Or modelize the operator.
No car, you don't.
Sorry?
No car, you don't. No car?
I didn't know. I'm in the front. Yeah. So also, if you are clever, you put this sensor. If you want a 3D model, you put this sensor on a. So it's measuring this plan. You have an axis here. The motor is rotating like that. It's throwing the laser in that direction. But if you put an axis like that and do like this, you will scan also like that. So this plan, and you can have a model with 3D. That's pretty nice. So the point is that you have this sensor that exists in real life. You can buy it. It's a Hokulus sensor. You can have the specification of the distance it can detect and in which angle is able to detect distances. So I take this. This is a proximity sensor. I parameterize it to be a ray that with the distance of the maximum distance detectable, it's written in the specification. You can write that down and reuse that and parameterize that like that. Then, like the real one, I put that on it's a rotating mirror, but you don't want to put a mirror, you just directly put the laser on a joint. So, I measure that, I rotate, measure. And also, this is the shape, just to be looking pretty, for the simulation. You have the shape, and you can make a tree like this, where you have the full sensor working. No, not yet, because we need to have the control script. The control script is attached to this object. And what is it doing? It is managing I want to read the laser. Now I want to rotate the motor from 1 degree, reading again, reading 1 degree, reading again, etc., etc. And put all those data, those distance data into an array, and make that available for all the script to be able to read. Also, I want to manage the fact that I'm able to show, I want to display the laser or not, this kind of things. Everything is coded into this embedded script. So we're gonna go up to the next step is to go and we're gonna be doing this robot, or kind of this robot, and we're gonna use most of the three modules that I presented. So first we will be modelizing and building the two-wheel robot. Then we will be tuning its dynamic stability, to make it stable, to tune the dynamic parameter to make it stable. And we will add some sensor capabilities. That I don't think we will have time to do, but it's very easy. And then we will put some control, we will use a script in order to be able to control it and have a basic automation, autonomous behavior that we're going to do right now. So, still didn't find any solution. We didn't want to find any solution. I don't know what happened. The professor effect is called, when you want to do a presentation to your professor and the professor is coming. Yeah, the professor is coming and you're showing like, hey, look, it's working fine, and it's not working. That's the professor effect. So now I'm a professor myself, so obviously nothing is working anymore. So that's the problem. Okay. So, let's go. You have VREP open. Everybody is ready to go for a VREP experience. Everybody does have VREP open. Let's go. So, this is VREP environment. So, what you have, if you click on this little robot here, you can see everything. Everybody can see on the left side. Oh, maybe I need to. Like that? It's better? Okay. Everybody can see the full window? Okay? So if you click on this little robot here, you will have the model browser opening. So in there you can see, you can navigate a little bit in there. You have some household, nature, office, folder, conveyor. You can navigate in there. And we even have like mobile robots, like several mobile robots. This is actually the ball robot that I was telling you about that I couldn't show. So you can drag and drop robots and stuff inside the simulation, and when you press play, the simulation is starting. And for instance, with this one, I can select. Okay, I have three important icons here. This one is to pane. So if you click in the scene and move around, you will be translating the position of the point of view. Okay. This one is rotation. So if I click somewhere, I will rotate around this thing. Okay. Or earthquake simulation. This one is to if you click and move the mouse, we will zoom in, zoom out. You can also use the mouse rolling button if you have a mouse, and if you have a touchpad, probably pressing the two button left and right and moving your finger around would be doing the trick. Yeah, that's it. I have a Mac, so it's 2 fingers and it's but no, normally if you have you press left and right button and you can zoom in, zoom out. Okay. So press play for the simulation if it's not done, and then you have here, this button is to translate an object, to change the position of an object. So I'm going to take this one and select, I don't know if you have the robot on your simulation, but you can play around with it. For instance, I select this green target stuff, and I can move it around, and you can see that, whoa, there is a good balance control with this robot. Let's do a nice earthquake. Yes! I was very mean to it. Okay, so you can select objects, you can delete them, you can add them, you can put some more robots. You can press stop the You can stop the simulation if you want. So you can see that we have like a lot of different kind of robot. In the university you have this one, this mobile manipulator. You have this one, a lot. Congratulations, you are the second university that has the most number of now in the world. That's an achievement. I mean, you have a lot, -1, because I'm living in Costa Rica, I told you already. I'm taking one.
I have now in this lab.
Okay, yeah, no, you don't have anymore. It's going with me. So you have several of you. Any question? Please, if you are not following or if you have questions, just ask me, okay? Like we're gonna go through the use of the software. So you have even flying robots like this robot. Like if you're dropping into the software and if you press play, it's the same. There is a script that is controlling the position of the robot, like the thrusters of the robot, of the four thrusts, in order to track this green sphere or to actually follow it. So it's the same. I can go like that and it's following me, and I can it's fine. You can try to trick it. Okay, so those are robots. Even this one, which is really nice. This is the one that I told you that is doing some scaling. Yeah? So it will be working, and there is a behavior already programmed in it. And if you want to see how this is programmed, you can click on this icon here, which is the scene hierarchy icon. That will show all the hierarchy of the scene, any object in the scene, how they are linked together. Like, so if I took this rolling robot, yeah, skateboard. If I press this little plus, I open the tree, and you can see that there are like plenty of things in there. And there is actually this one. This is a control. This is a control script. So you see that that's pretty neat. There's not so many stuff, so many lines of code. Only 120 lines of code, and the robot is able to do all this. Okay? Perfect. Okay, now let's do it like this for a moment. So to repeat, we have like those three icons to change the position of the viewpoint. Those two are to change the position, and orientation of the robot. Okay. Now, if you are in let's go back to position mode. Or let's take this robot. I want it to go up. So if I press, you see that. If I am in the translation mode, if I press the button, I can move it around in this plane. But if I want to go in the other plane, I have to keep pressing the motion button, the click. You click, left click, and you press control. And then you see, there is this, you can see that. If I press control, it will be giving me the opportunity to go up and down, okay? Good, we're good? So those are the basics manipulation tool for VREP. Also, now you have we can close the border. Now you have the scene hierarchy open. If you double click on the name of the robot, you will be able to edit the name for the you can change the name if you want. Okay? It's not that easy to do. You have to click twice, and it will open the stuff, and you can. If you click on an object, oh, that's going to be a problem. That's not opening because of the multi. I installed the beta version. We might have some bug in our beta version, so I should not have done that. Okay. If you double click on one object of the scene, you will have this window that is opening. You see that there is a. So I clicked on this cube, which is a shape. This is a joint, and you see that the context changed if I click to another one. This, let me find the sensor. I don't have any sensor here. Yeah, I should have taken another sensor. Okay. So if I click on this, if you click on this little script, it will open the script editor. Okay. If you double click on a camera, it will open another scene object property. But all of them, they have this common thing here. Common. You see, those are buttons you press and you open another windows. If you go to like this force sensor, this is force sensor, so I have some data in here. Okay, let's move on. Okay, please go to File, New Scene. Okay, so that we have a new scene. Okay, you can close the model browser, click in here. Okay, File, New Scene, click here, model browser, and let's start to build our first robot. So we want to design this robot. Everybody can see here. We want to design this robot. This is a differential drive robot with 2 wheels. Actually, there is a third one. We'll see why. We make it simple. It's basically a cube with 2 cylinders for the wheels, and we'll have 2 motors, left and right motors. Okay. And once we will have made this model, we will change the dynamic to make it stable, and we will have our first control script to be able to control the behavior of it. And also we have a proximity sensor here, which is important. Okay, let's go for it. Okay, so let's start. First, we want to have. Let's build this. You see, there is the number 1. Let's build the body of the robot. It's going to be a cube. So you go inside the scene. You press the left. So you double click. My mouse is just killing me. Selected the. Okay, don't remove the page. If not, you will have the same thing. So you right click. Right click. It will open. I think it's right click with normal computer, not Mac. Mac is two finger because you have only one button. So right click. And then you can go to Add, Primitive Shape, and we're gonna add a cuboid, which is basically a cube. Okay? Then it will open this primitive cuboid window, where you can define the size in meter of the cube in the direction X, Y, and Z. Here, X, Y, and Z. You see? X, Y, and Z. X, Y, and Z. Maybe on my head, you don't work. X, Y, and Z. So let's. I wrote that here the specification of the cube that I want to have, the size of the body. So we have like 15 centimeter by 10 centimeter by 20 centimeter. Okay. So let's do that. To do that in X, as you see, I have the same. Like this. Let's change. Let me change the orientation for simplicity. Yeah. So now we are like. I did the orientation here. Okay. So add the primitive shape that is a cuboid, and in X we have 0.15. So I type 0.15 in here. Or 0.15, it's the same. It will write that in this format, which is, it's exactly the same thing. In Y, we have 0.2 meters, so 20 centimeter. And in Z, we have 0.1 meter. 0.1. Up. 0.1. Okay? Everybody did that? It's a pure shape. We go and okay. We have a nice cube. Nice cube. Okay, everybody does have that? Who's following? You can move around it and you can see that it's resting on the ground. But that's not what we want to have. We want to have we want it to be at 0.03. We want to have 3 centimeters under the belly of the robot. Okay? So in order to do that, we need to translate the position of the robot. How to do that? With this tool. Here.
What tool?
Too late, I'm not showing again.
I have to record this?
This button here, okay? See the button? This is the translation tool I showed you. We played around with the target earlier. So here it opens. So you can model, you can move the robot with the body with the mouse if you want. But we want to be precise. So like you use CAD models, CAD modeling software, and you know that it's better to use to write the position, the coordinates of your things in the software. So in this section you have it's called relative, but it's the absolute position in it. The position related to this to the initial frame, to the 0, 0, 0 of the word, which is like right here actually. So either you put the absolute rotation here, or the absolute position here, or you make some translation. So this is translation considering the word frame. This is the word frame, okay? So we want to go into so here you have the robot, the body that is like on the ground. We want to translate it into the z direction by 3 centimeters. So that's exactly what we're going to do. We're going to put here 0.03. We are relative to the word frame, and we are clicking once translation. You see? It just translated there. If I press twice, it's too much. So I have to go minus here. Here we go. Okay? Good? Everybody follow? Okay, let's go for wheels now. Let's put some wheels. So, it's the same, right click, add, primitive shape. Wheels are cylinders, okay? So, cylinders. Now, my cylinders, it's going to be like, in the x direction would be the diameter, in the z direction would be the thickness of the wheel. And I put it here like so, 0.1 and 0.01. So let's do that. Here, 0.1, this is the diameter, and 0.01 in here. Okay? Once it's done, I click OK. As you can see, if I zoom in and rotate a little bit, it put the wheel at the 0, 0 position, but on the ground. 0, 0 is x and y, and half the width of the cylinder is here. Okay? So now, our wheels are actually. I forgot something about. Sorry, I forgot something also about the translation of the cube. Here you can see that we just did that, but the cube is not here. The cube is a little bit like there. So we have to do a translation by 0.07 into the minus y direction. Okay? See? This is here we have 0. Write that down. The frame is here actually. This is z, and this is epsilon. Okay? So the cube is not centered. The center of the cube, we control the center of the cube. So it's not, we did some concession here, but we have to go a little bit backward. Okay? So let's do that. To do that, well, you click on the cube, you select the cube, okay? Once the cube is selected, you click on the position, the translation window, okay? Here, just put 0 because we don't want to translate anymore into the z direction, so 0. And we want to do a translation in the y direction by minus 0.07. So here I will be writing minus 0.07. Okay? And I will be clicking only once. look here. Look what is going to happen. The behavior that you want to do, and exactly that. Yeah, it's exactly what we wanted to do. Okay. So we have the 0, 0 point is 0, 0, 0. The reference frame is actually here. So, okay. Let's keep on going. This is pretty simple. So now let's get back to the wheel. We want to locate this wheel. We want to put the center of the wheel. We have the wheel here with the center here. We want to put this at this point. This point is in x. Yeah, this is x. We are like minus 0.1, and the other wheel will be at 0.1. Okay, in the x direction. It's 0. We are the center of the wheel. It's at the 0 in y, and we have like 0.1? No, 0.5. It should be 0.5. Yeah, 0.05 the radius for z. So it's going to be translation. Here, you want to put and instead of making some translation, we can actually put the real coordinate, the real coordinate of it. So the coordinate of this point would be in x 0.1, in y. In y 0, and in x 0.05. Correct? Yes. Maybe correct. Now the orientation is all wrong. Yeah. We don't want the wheel like this. No? So we go to. Everybody follow? I'm going too fast. Okay. Where are you? Sorry. Yeah. Okay. Okay. You want to see the position of the translation?
Hey, what is?
No. So here, 0.1, 0, 0.05, and click, and you don't have to click anything. It's doing okay. So automatically. Okay. Good. Okay. Now the orientation. The orientation is wrong. So we go on the orientation tab, orientation rotation tab, and here you have alpha, beta, and gamma. Those are the rotation around the x, y, and z axis. So we want to rotate like this, right? We want this wheel to go like this. So we want a rotation around the green axis, which is the y axis. Okay, so we want to go 90 degrees around the y axis. Correct? So the y axis is beta. Here we just write 90 degrees, and worked. Okay? Let me see if it is correct. Yeah, we can have the robot diagram. It's not exactly what I wanted to do, but it's okay. I mean, on the right line. It's a little bit different than that. Here I didn't measure properly. I don't have it's not up to scale. Okay? Everybody has the first wheel. That is actually the right wheel. This is the front of the robot. Everybody's okay? Everybody's okay? Okay? No? If nobody is saying anything, I will consider it so yes. Okay? So everybody's okay? Okay. Nobody's saying so good. So this, you can see in the scene. Yes?
Pamela has a problem.
Okay. What do you have? Not coming. I'm gonna check if everybody's. Okay. Okay. Yeah. Okay. Let me correct you which one. So this is the position of the robot. Okay. So let's put it into 0, 0 here. Let's finish it. 0, 0. Okay. Here. So we wanted to make a translation to the Z by 30 centimeters, so it's 5 centimeters. And okay, and also going translation by 7 centimeters minus 1.0. So here we have the rotation. Here, for the rotation, if your wheel is still like that, you want to rotate 90 degrees. So you just put you click on orientation, or you can select directly this button here.
Which one?
This one. Either you click here or you click here. Okay, the same. And you want a rotation by 90 degrees. 90 degrees in the Y, so it's beta. Beta angle, you write 90. French keyboard, 90. And you will rotate. Okay? Everybody's fine? Okay. We have cuboid and cylinder. Those are not ugly names. Let's selection the name of cuboid and erase it and write my underline robot. Mi robo. Mi robo isuko robo. My robot. Okay, and now we have the name of the cylinder of the body that is my robot. Cylinder. Cylinder is not a good name. Let's write that. This is the left or the right wheel? This is the right wheel, right? Yeah, right. Right wheel. So let's write right wheel. Enter. Okay? Everybody's fine with writing the names?
Yes.
Now, maybe we need another one, another wheel. So, I'm going to show you something very nice. You already placed one wheel properly. So now you select the wheel, you do Ctrl-C, Ctrl-V, and you copy-paste the same wheel at the same place. Okay? Let's modify the name already. Like this one, I want that to call left wheel. Left wheel. Okay? Am I going too fast? Everybody's fine? Please tell me if not. Okay? And now, let's move this wheel, this left wheel that we selected, into this place here. We have 0, 0 here. Yeah? So, I want to move. So, I press this button, and I see that the position is 0.1, 0, and 0.05. Okay? But I want the wheel to be here. So, basically what I need to do is modify the position to the other side of the frame by putting the minus here. And then, wait! We have a second wheel. Too fast? Translation, put the minus here. And obviously you put that on the other side of the... Okay? The robot is taking shapes. Okay? Now look, if I press play, what is happening? What do you think will happen if I press play? Who is going to be able to guess? Nobody? Look, look, look. This is nice. We have a nice robot. Yeah, why? Why do we have that? Because we have like some floating element, like some floating heavy body in the air. When I press play, I will have a dynamic. This is a dynamic object. So the dynamic engine behind the dynamic engine in the dynamic engine module will handle the behavior and dynamically of this object. Make it fall, obviously. That's what will happen in real life. Yeah? Where do I know about this dynamic engine? Here, you see, this is dynamic engine called Bullet. You have ODE, Vortex, and Newton. I don't like Bullet. Let's select ODE. Okay? See? Okay? Perfect. ODE. Now, okay, we press play and doing the same thing, but the wheels, they are not moving around. They are like staying at the same, which is a much more realistic behavior from my point of view. So now we are in the we are in the dynamic. Dynamic means that we handle weight and these kind of things. So we don't know the weight of. How do I know the weight of the body? I want to simulate something close to reality. So I need to know the weight of my body. I need to be able to specify that the real robot will weigh that much. So if you click on my robot, the square icon, the cube icon here, double click it, and you will be opening this scene property window. Okay. Then you click on Show Dynamic Property Dialog. I have all of this. So this is the property dialog of the robot. If I click here, the robot will not be dynamic. It means that if I press play, nothing happens. It will not fall because it's not a dynamic object. It's just an object that is there. Okay? So we want that to be a dynamic object, and the weight is 3 kilos. We don't want this is a small robot. It might be like way less. Actually, I brought it here that I want the cube weight, my robot, to be 0.1 kilo, 100 grams. This is barely more than enough. So let's change it. Like we put 0.1 here. Okay? The wheels, it's the same. If I click on the wheel, the right wheel, I see that the wheel is like 0.78 gram. So let's make that, just for the fun of it, 50 gram. So 0.05. Okay? Okay? And the other one too. I select it, and I want that to be 0.05. Any question? Everybody's following? Okay? Okay? Perfect? Keep on going. So now if I press play, I have the same behavior, but now with the proper way. So why does that fall? It falls because there is no contact, there is no joint between this and the wheels. So that's why it's falling. So now let's put some joint. The joint are going to be the link, the physical link, and also the motors that we're going to be using for making those wheels rotate. So let's do that. How to add a joint? I right click in the middle of the scene and then add, and I have something called joint here. Okay? We want to put a revolute joint, which is a motor. Revolute joint. Oh, look, it appears at the 0, 0 position. The only problem is like it's not oriented. The revolution axis is the Z1, so that's not how we want to rotate it. We need to make this joint rotate. So how to do that? We need a rotation about which axis? X-axis, are you sure?
No.
The x-axis is the red one. If we do the x-axis, we will rotate like that. We want to rotate like this, like this. So this is the green one. This is the y-axis. So 90 degrees in the y-axis. So selecting the joint, it's the same than before. Go to the y-axis and go 90 degrees here. 90 or minus 90? Maybe. Let's see. I think it's minus 90. But it's okay. It's like that here. Okay? So now I have the axis the axis is correct, but the position of it is not correct. We need to put that at the same. We need to put the axis, the motor in this direction on this axis, coincident with the axis of the wheel, right? So to do that, there is a very nice trick. Look, you select the joint. You press Ctrl to make multiple selections. You select the first wheel, the right wheel, for instance. Okay. So you see that it's the bounded box here is yellow. So it means that this is this was the first thing that you the first thing that you select. And if I select more stuff, you see only the last thing I'm selecting will be white. Okay. I can deselect by re-clicking. Okay. So selecting the joint, pressing Ctrl, selecting the wheel, and now, if I go to position, position translation, I have a button Apply to Object. What does that mean? When you select an object, it will show these coordinates here. Okay? When you select another object, it's another coordinate here. Now, if you do some multiple selections, you will have the last parameter of the last object. So apply to selection means that all the objects that are selected will get the properties, these properties, the things that are here, of the last object selected. So by clicking like this, I'm putting the motor at exactly the same position of okay? So this is the right motor, right? So I deselect by clicking somewhere else, select the motor only, and let's modify that and write revolute joint is not proper enough. It's right motor. Write it like this. Right motor. What is that right? Oh, okay, but it's right motor. No, here. Oh no, it's just wheel. I forgot to write about the motor, but it's okay. Right motor, okay? Like this. Right motor with capital letter. If you don't write it like that, just remember that it's not like that because the code it will be important later for the code. And enter, okay? Right wheel, right motor. Now, I want to do the same with the left motor. How do I do that? Left motor, I select the right motor, I copy paste it, I change the name to left motor, okay? And the left motor needs to be with the left wheel, right? How to do that? Same thing, select the left motor, control, select the wheel, and apply to selection. There we go. Okay? Now this is pretty ugly, I guess, like to have those motors shown like that, I mean those joints. I would like them to disappear. Don't you agree? It would be nice. It would be nice. So, if you want to, we want to put them to another layer of visibility. That's the real term. So you click on the right motor, and in common, in the common folder, you have visibility layer, and you can see that it is affected to this layer. This object is visible into this layer. I can make it visible also here, 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 in whichever layer you want, but let's do it like this. And here you have a button which is like to be able to select which layer you want to show. So if I deselect this layer, every object that is affected to this layer will not be visible anymore. If I do that, if I invert here, I see only the stuff that are with these layers. Okay? So I don't want this photo to be appearing, so I just select and deselect it here. And same for this one. Select it here and deselect it here. Now I have this one. Everybody, it's clear for everybody? Everybody's okay? Pamela? Okay, so now we have the left, do I have the left motor and the right motor? And you can see here in the hierarchy keep seeing that it's light gray. The stuff that are not appearing in the current configuration of visibility layers are in light gray. Okay, so now we have buttons, we have joints, and we have the object, the wheels and the body. If I press play, what will happen? What will happen now? What do you think will happen if I press play? Don't press play. Don't cheat, don't press play. Everything will fall. Oh, it's the same. Why? Because I didn't say what is linked to what. This is important. You see, everything is at the same level here. I want to have a tree. I didn't say that the wheel is linked to the body and this wheel is linked to the body and this, etc. is linked to that. I didn't say that, and it is very important. So, how do we do that? We have where is it? My robot is here. This is the main body. We want to link that to each of the wheels. Okay? So I select. But to link object in direct, you need to link that with a joint in the middle. Okay? So I take the right motor. You select the right motor. You click, drag and drop it over the my robot object. And you see, it's a son now. The right motor is a son of the body. Okay? Now if I take the right wheel, I can attach the wheel to the motor. Okay? Now if I press play, point. Okay? This is normal behavior, okay? So now let's do the same with the left motor. Left motor, you put that as a son of my robot, the body, and the left wheel will be a son of left motor. And if I press play, what will happen? What will happen? Nothing? It will stay like that, finally? Yes? No? Who say yes? Who say no? Okay, the rest of you doesn't have any opinion. Abstention, everybody. Not even. Now look what is going to happen. Oh, point. Obviously. Because we have the weight that is not on the line of the... So obviously, so what does that mean? And this is normal behavior. if you make this robot, exactly that will happen. So what we need is a point of contact here, a rolling point of contact. So we're going to do like put a ball, a small ball, a rolling ball, just to have a third point of contact to have the triangle of sustentation. It's called. Okay. So let's do a ball. A ball is like right click, add primitive shapes, and sphere. Okay. And I already put the size of the ball, and I forgot to put the distance here, but it's okay. Let's do the size of the ball would be about the size of the gap that we have between the body and the ground. So it's 3 centimeters. So let's put a ball of 3 centimeters, 0.03 here. Look here. If you don't want to double click into properties, etc., you can already set the size. No, you can't. No, I didn't say anything. Okay. So now, where is the ball? I don't see it, but it's here. Good. Oh, here it is. Good. Now we want the ball to be on the back, right? So you select. What you can do is actually select the ball, and drag and drop it if you want. Yeah, like around here. Okay. But see, it's okay, but it's not in the center. It's a problem, eh? It's not really a problem, but we can arrange that. You select the ball, and you put you correct the coordinate in x. You don't want to have something in x, so you put 0. Here we go. No, sorry, it was not x. It was y. No, it's x. Hold on. X. No, x is 0. No, it's x. Just a perspective point of view. So, what? No, it's not what I want. Okay, sorry. I don't know what I did. I do it again. I put the sphere around here, and I can see that. Oh, it's center. It's center but changed. But let me check. Yeah, I said X, but yeah, I modified Y. Yeah. So yeah, I'm okay with this configuration. Okay, so just put the X factor of the position of the wheel to 0, of the sphere to 0, and then the Y position. Well, you put it around here. Okay, or you can write it maybe minus in the Y translation. It would be minus 0.2, minus 1.7 or something like this. Okay? 1.5. 1.5. Okay? Everybody's there? Everybody does have it? Now if I press play, what will happen? Yeah? Pamela? You want to say? Okay, but it will be okay? Are you sure? Yeah, it's okay, but no, it's not okay. Because now if I drive, what will happen? Yeah. Okay, let's do that. Okay, let's do that. Let's drive the robot. That's going to be an interesting behavior. So, double click. Let's try. Everybody's is in this configuration. Okay. Double click in the left motor. That opens a join property, okay? Now, show dynamic property dialog. Now, this is actually the properties of the motor itself. So, I'm going to enable it. Yeah, this is not a passive join anymore. Now, this is a motor. I will write eventually this, like lock motor when we are in 0. It means like it's not a back drivable motor. And I will put a target velocity here of 10 degrees per second. Okay? Okay? 10 degrees per second. Let's do that on the other wheel too. Motor enable, lock if 0, and 10 degrees per second. Okay? Now what will happen? What do you think will happen? Yeah, exactly. Like the robot will go front, because this is the model that Andres showed, that if we put left velocity and right velocity to the same, we have the linear velocity, which is the average of both, like it was VR plus VL divided by 2. So the robot will go straight because same velocity on both the wheels. And exactly what will happen is what you said, I guess. Oh, Boom. Yeah. But the other way. So that's when I said like let's turn the motor by 90 degrees. It would have been better to put them by minus 90 degrees. So either you correct that by software or you correct that physically. Let's correct that physically. It's a pain. I will correct that by software. Okay, so as you see, the wheel is independent, and the ball is independent from the body because it's not inside. So I need to put the sphere inside the motor, under my robot. But to link two objects, I told you that we need to have a joint. Let's not put a joint, but let's put a force sensor. That's a nice. It's the same way, the same thing. So we do like add force sensor. It could be a joint, but force sensor will do it. Force sensor. Okay, the force sensor is here. So I select the force sensor. I select the sphere. I want them to be at the same place. So I press the location button. Okay, and apply to selection. Boom. Okay. And I click in the void to deselect everything. But it's ugly to see this sensor, so let's hide it. So force sensor, I double click on it, I go on command, and I put that in another layer. And now I have a robot, okay, like this. Now I need to rush because we need like 1/4 of the full tutorial. You're not hungry and nobody's going to lunch today, so it's okay. Force sensor is going to be under my robot, a sphere, a son of my robot, and sphere is going to be a son of force sensor. Let's modify sphere, it's an ugly name. I'm going to call that ball wheel. Ball wheel, okay? And if I press play, what will happen? Exactly. Wow, look, we have a robot. That's cool. No? Isn't it cool? Everybody's there? If I go and see your computers and press play, the robot will do exactly that? And I told you, there's you're graded after that. It's a part of your credits. You don't know about that? Everybody's and with a high coefficient. Everybody's there? It's okay? Okay? So now we have a fully functional robot. We need to put some behavior in it, right? We did put some behavior, not in the script, but directly a constant. We put a constant of velocity into each model right now, right? So we did like put the same velocity left and right, it goes front. Now if I put the same velocity, the velocity on the left wheel, let's say 10 degrees per second and minus 10 degrees per second, what will happen? It will rotate at the point. Yeah? The instantaneous center of rotation will be here. If I put 10 and 5, what will do, robot? It will go like that. And where will it be rotating? I mean, what will be the point of rotation? It will be here, the instantaneous center of ICC, instantaneous center of rotation, ICR. I don't know. Anyway, so it will be like that. To detect, it's easy with the model. You just go, you put your vector of velocity of 10, vector of velocity of 5. You will have a vector of velocity of 7.5, half the way of that, and you will have an angular velocity also. And you will be rotating around this center here. Let's do that, just to see if it works. I'm going to select the right wheel. And I'm going to go moving that at 5 instead of 10, okay? And I'm going to play. Okay, I'm going to show you something else which is, I want to see the robot from the top. So I go to this button which is page selector, and I have plenty of views. So I'm going to take this view. And now I see the road from the top. I can zoom in. This is nice, eh? And what happened? My graphic card is tricking me, and that's a problem. Yeah. This is my graphic card. Don't buy a Mac. And install it, and don't buy a Mac and install Windows on it. Don't, it's a bad idea. It seems to be a good idea, but it's not. If I do that, maybe I know how to do it. It happens sometimes. You see, yeah, it's working everywhere. Okay. Come back. Let's get back to it. So we can let's put 0 to the velocity of each of the motors, the left and the right. 0. Okay. Now, no, that's not what I want to do. Now let's put some behavior to this motor. Yeah, you've seen that we can edit manually the windows and put some velocities to the motor, but we want to control that from a script, not doing it manually. So let's do that. You select the object you want to attach the script. It could be any object in the scene, but let's make that the robot. Yeah, that would be more my robot script. My robot script would be better. So you right click. Okay. You select my robot. The line. You right click on it, and you go to add and associated child script. And we're gonna go for non-threaded. I'm not gonna explain the difference between them, but basically go from non-threaded. Okay. And now you can see that behind at the end of the line of the object in the scene hierarchy, I have this little icon. If I double click it, it's opening some Lua code, already installed Lua code. So what is in green is some comments, just to help you out. Please erase it. Okay, we erase it, and I will be telling you what it is. Okay, everybody's here? So it's written, do not write code outside of this if-then section below. Okay, so don't do it. Here, we have a specific part of the code which is called initialization. In there, you put like everything that is initialization related, like stuff that you want to do when you press the play button. This script is going to run like several times, like until you press the stop button. And in this part of this section, it will be done only once at the initialization. And in this part of the code, it's called cleanup, so it will be done only once at the moment you press stop. When you press stop, if you need to do some stuff, I don't know, saving something or whatever, it will be, you need to put the code here. Now, you have like those two sections, actuation and sensing. Sensing is done several times during the simulation, and actuation is done only once in one simulation step. So, what we're going to do is put some code here to actuate for us the sensor. But how, the motors, how do we, first you have to understand that any object in the scene is identified by its handle. A handle is a number that VREP is assigning to each of the objects. Once you're creating an object, there will be one number. Another one object, it will be another number, etc., etc. You don't know this handle. You don't know it, so you need to get it. So how to get it? If we want to interact with the motor, we need to have the handle of the motor. So to do that, I go in the initialization, and I will write the code. I'm gonna tab. I like to be like that. If you don't want to, and I'm gonna write left motor handle. This is the variable name is equal to the handle I want to get, and for that I have a list of functions that I can access by in the help topics. Help topics. It will open the manual. This is the VREP manual. And if you go to write code in and out VREP API, regular API, You have the list of all the functions by category, like for instance. And here you have the list of category of functions. All the file operation related functions are script here. General handle retrieval. General handle retrieval. That's exactly what we want. The sim get object handle. It sounds like those things we want to do. Right? Get object handle. And here we go. And here you have a description of what this function is doing. Okay? So let's do sim get object handle. And basically it says that it wants a string that is the object name. The object name of the left motor is left motor. It's written here. We wrote here left motor. So I put under brackets left motor. Be sure that you write it exactly the same way. If not, you will not find it. Okay? So now I have this number, this identifying number into this left motor handle. I select this line, I copy paste it, and in order to save some time, and I write right motor handle. And here is right motor. Right motor. Okay? Everybody's there? Okay, now in the actuation section, we're gonna tell to the simulator, put this velocity to this motor. How does that work? If you look in the recipe of this one, we don't have time, but if you look into the manual, you will have a function that is called sim set joint target velocity. What does that mean? I want to put a target velocity to the motor. So we want which motor? We want the left motor. Left motor, we want a handle. Handle of the left motor is called left motor handle. And the target velocity a number. We want it, let's put 10 degrees per second. You remember 10 degrees? So if I put 10 here, it's not going to work because here it wants radians. So you have to convert it. Okay, so 10, how to convert degrees in radian? You multiply by math.pi or 3, or you can write it if you remember, that's 3.14, but math it does that for you. And you divide by 180, okay? So if I do that, for the left and for the right motor, okay? If I press play, I can see that the robot is going into the other direction because the motor is inverted, but it's okay. Okay? So if I want the robot to go in the other direction, you can put minus here and minus here. And if you can play, you go into this direction. Okay? So now we have a way to control the robot. Okay? Let's say that this is the front of the robot for simplicity. Now we want to have some autonomous control of those velocity. So for that we need some kind of sensor to close the loop. Okay? So we are going to put a proximity sensor in the nose of the robot. That would be here, the opposite of that, but it's okay. We're going to put a sensor that will be able to detect if there is an obstacle ahead of it or not. Okay? So let's do that. With the right click, add proximity sensor. We want it to be a ray type proximity sensor because this is the sonar, you know, the sonar. So code type, oh look, did one, but it's not located at the proper place, and it doesn't have maybe the proper parameters. So let's put that in front of the robot here. So to do that, you go here, and you can translate it here and translate it in that direction. Remember how to do that? Press click, you click, and while you click, you press control and it will change the direction. And you can put, let's say, let's put it about here. Okay? Everybody's okay? Now the answer. Now rotation. I click. It's the same. If I do that, it will rotate like that. I don't want to rotate like that. I want to rotate in the other direction. So in order to change the rotation, I click control. This is the one I want. But if I wanted another one, I need to click another time. Release and click. So if you click and release, it will change the angle of rotation. And then you can rotate it 90 degrees. Okay? now you can see that we will with this configuration you can see that this is the red zone is the detecting point. Do you think that with this we will be able to use this configuration or not as a sensor? I mean, that's not going to work because we're going to detect an obstacle which is the ground all the time. Okay? If we put a sonar that is looking like that, we detect the ground. We don't want that. Okay? So we have to change the type of sonar we want. So to do that, you double click on the icon of the sonar. Okay? Here. Abela, you okay? I don't see you anymore. You're here, okay. Good, you're good? Okay.
Most famous.
Sorry, you're the other one, I know the name, I just thought I would target someone else. Okay, now we need to change the volume parameter, we want to change the shape of the volume. So, show volume parameters, okay? And here you have volume type, cool, yes. Offset, that would be like from where we start to measure. 0, yes. Range, 30 centimeters. I put there the range I want it based on the hardware I bought. So here, you won't be able to see anything. Here there is the range 15 centimeters, radius 0.0, and the angle 30 degrees. This is the important part. Okay, 30 degrees. So the range 0.15, the radius. 0, it's okay, and the angle not 90 degrees. You see, there's a cone of 90 degrees. We want 30 degrees. Oh, that would work, right? We are not detecting the ground anymore. Okay. Too fast? You good? Everybody's good? Okay. So now, if I press play, what will happen? The sonar will stay at the same place. Don't forget to take the sonar and make you a child of the robot. Now when I press play, it will follow. Okay? Now let's put some obstacle to see if it will be detecting or not. Add primitive shape, cuboid. Let's put a cuboid in front of it. And let's put a cuboid of 0.5 by 0.5. 0.5 by 0.5, okay? And let's take it, we translate it like in front of the robot, okay? If I rotate here, it's in front, or not really in front. Okay. I put it here. Now, this dark red detection cone will be turning pink if I detect something. So let's see if it goes. It should turn pink when you touch, and it's not doing it. Why? Because you have to know that by default, the cuboid is supposed to be a dynamic object, not it's not detectable by default. So it's collidable if I go there. No, right. It will be collecting. Oh, we are collision, but it's not detectable by the obstacle by the sonar. So in order to make it detectable, you select the cuboid, you go to command, and here you have collidable, renderable, measurable, detectable. Just select everything so that it will be seen by the camera, it will be detected by the sonar, it will be measured and collidable also by the motion planning algorithm. Okay? And now if I press play, look, when it's going to detect it, oh, you see? Have you seen? It turned red, pink. It turned pink. That's okay? See? Pink, 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 pink. I wrote it down. Okay, so now programmatically, let's do something to detect, to tell us when we detect something. Let's make this happen. So in order to do that, you go to the script, double click on the script, okay, and we go on the sensing script here. Okay, let's find out if there is something called read proximity or something like this. Read proximity. Oh yeah, read proximity sensor. Here we go. We have a function that is called sim read proximity sensor that reads the state of the proximity sensor and return 0 or 1, returns eventually a distance and even detecting points. Okay? So we just want to know if we have if we detect something or not. So we're gonna put like detected like a result res equal sim read proximity sensor. Okay, sim read proximity sensor. So it's written here, number, result. So I could put that result, distance, and something else. But I'm not. If I don't want those parameters, it will put them into the order. So the first one will be result. If there is something on that, and it wants just a sensor handle, just the handle, the identifier, the identifier of the sensor. We don't have it. We need to put it here. So we're gonna show that we're gonna put that sonar handle here. Is equal to sim get object handle. Okay? And the name of our sonar, which was sonar. Proximity sensor. Let's change that to sonar. Sonar. Okay? I'm too fast? Good? Okay? And then here I can write sonar. Okay? Now sonar handle will be the number associated to this object. Okay? And if I put sonar here, this is a sonar handle here, I will be able to read the distance, and if there is a 0, I don't detect anything. If there is a 1, I detect something. Okay? As the manual said. Let's verify that. If res is more than 0, then I want to display, there is a function called sim at status bar message that allows me to write something in here, in this part here. Okay? So I am going to write detecting. Okay? And yeah. Everybody understand the code? Everybody wrote it? Pamela? Yeah. Until someone else is introduced to me. You good? Okay, let's see if it works. Let's see if it works. I press play, and look here. Simulation started, and detected. Yeah, we detected something. So we are able to detect something. Okay. Now, even the distance. Eventually, you could write the distance. To concatenate strings in Lua, you do like this. Dot dot, and then you can write this here. So let's make a space here. Okay. If I do that, look here. Detected and the distance. Hey, that works. You see, the distance is written in here. That's great. Okay. So now let's make a very basic controller. That would be, we go straight, and then when we detect something, we will be backing up with some angle and go slow. Okay? Let's try to do that. So, how to do that? We go in the actuation part, and we write if, let's invent a tag, detected, that would be a tag that way. Is true, is false, then I'm going to go straight. Okay? Else, I'm going to go backward. Here, okay? To go backward, and backward with some angles. That works with C, Control V. Let's go -10 and 0. Oh, and -10 and minus 5. Let's see if it works. Fine. Now I need to select, okay, so I have a Boolean parameter here that I need to initialize. Detected, I'm going to initialize it to false. I set it up to false, okay? And if I have detecting something, if I am detecting something, detected, it's going to be able to true, okay? And if I'm not detecting something, false, then get inside there. And I need here to be sure, I need it to go true. Yeah, if not, I might be in a situation where I never go back to normal. Okay, so this is the code. Everybody consider. No, well, let's see if it works before you type it out. Let's see. So when there's a detection, it goes out and it never stops. So because because detected should not be called here. Detected be true. This should be detected as well false, not true. False. False. Okay. Let's try that. Detected and this is the theory. And that doesn't work. Why? Why that doesn't work? It's on purpose, don't worry. I was expecting that. Why does that? It doesn't work because when we are detecting something, we are turning. So it was turning and getting out of detection and then go straight. But the thing is that this is smaller than this. The detection code is smaller than that. So the problem is that we're using this behavior as an algorithm. I will have that because at some moment I will not detect something, I will go straight, but I will have an obstacle here. And this is exactly what happened. So when you have this situation, it means what? That maybe your design is not correct. Maybe I need to put some more sensor on the side. Or maybe not. Maybe buy a sensor that is larger, or maybe I need to change the behavior of it. Like instead of when the algorithm here is doing the following, is like go from as soon as I detect something, you start to you change your heading. But the thing is not going even backward a lot because as soon as I go backward, I'm not detecting anything. So I go backward, rotating a little bit, just only a little bit. This is not enough. So maybe what would be more interesting is to put some kind of timer so that when I detect something, I go backward for a certain amount of time. Like I go strong, I detect something, I'm going like this and then stop, like for a while, and then I go front. You can do something like this. In order to do that, and let's do that, it's cheaper than buying several of those sensors and put them on the side. So in order to do that, to save some time, I'm going to pick up the code because we are already very late. So I'm going to have a backup until time. So I'm going to make a backup until time for the parameter. And then so instead of doing this detected false stuff, I'm going to erase it. I'm going to go with this thing. This, and what did I miss? So instead of having a detection state that is true and false, I'm having this. I'm putting this code. So I set up a backup up in town to -1. I could do something else. But okay. And if backup up in time is less than get simulation time is a timer, just like looking at the time. And I'm adding 4. If I detect something, I'm adding to this. I have a value of back until time that is simulation time at the moment of the detection plus 4 seconds. Okay. So if I check for back until time is less than the real time, I will be going backward, and if not, I'm going forward. Let's see if it works. It doesn't work. I have sync at velocity, target velocity, so when something is wrong, you have this happening here, and it's written in the. It informs you that you have a problem like 17 and 18. So let's see, like 17 and 18. That's it. Ah, okay, okay. Because left motor handle speed, yeah, I was going to 10 or more. Then -10 and -5. Okay? Okay. Let's try it. Whoa! That was fast. Why? Did I put some? Why is it that fast? 10, 10, 5. Ah, yeah. You remember I told you, take care, it's not degree per second anymore, it's radian per second, so I have to change my motor. Like I have to convert, I forgot to convert that into radian. Mat.pi divided by 180. Yeah, because that was a lot of radian per second. It was not 10 degrees per second, it was 10 radian per second. That was, woo! That was fast. Okay, let's see if this parameter is working. So the robot is working, and then 4 seconds. That's gonna be, that's a bit better, but I'm not sure it's gonna pass. Oh, no! So 4 seconds is not enough. So 4 seconds would not be enough. So to do that, I basically need to tune my parameters here. Like let's say I'm backing up for 10 seconds. Okay? That's going to be way too much. Yeah, by the way, this is 10 seconds. No, seriously, but this is because we are not in real time. It goes very fast as it can with the simulation. If we click on real-time button, the robot is going to go very slow. Because this is 10 degrees per second. Like 1 second is like 10 degrees, 90 degrees. It takes 18 seconds for one rotation of the wheel. Yeah, one rotation of the wheel is 10 centimeter diameter, so multiplied by pi. Anyway, that's too long. So what we need to do is, let's change this number. Let's write speed in order to not to have to change everywhere. Speed divided by 2, and that's it. And let's put only 4 seconds. That would be enough. 4 second backup, and let's say here that we have speed equal to 90 degrees per second, 100 degree per second, 100 degree per second. So every second I have half a rotation. Let's put one rotation. 360. Okay. So 360. So in 1 second I will have a full rotation of the wheel. So let's see if how that works. Ah, that's much better. Look! That's too much. That's too much. That's too much. Okay, so divided by 4 here. If I divide by 4, for instance, here, I'm going and here. That's still a lot. That's still yeah. The robot will go front and okay, so reduce. To back up for 1 second. only. Does work? And here we go, and we have a behavior. Finally! You want to see the code? You want to see the code? Yeah, you need some more tuning to be, maybe the behavior is not perfectly what you want, but this is basically the structure. So we went a little bit slow, but I wanted to go further. What you can do with your episode, this is just a very small taste of what you can do with VREP. I hope you liked it. To know, now that you are in love with VREP and you want to do that every day, you just go, I suggest you to go on help topics, okay? And go here. You check here, it's written tutorial, and then you have like a lot of tutorials. So you have the bubble robot tutorial, which is pretty similar to what we have done, okay? You will build this very nice looking robot, and you will learn about VREP, what the buttons are. You will have also an obstacle avoidance implemented, and you will learn how to make API, graphical user interface. For instance, if you check for robots like the KUKA robot, the U-bot that you robot, sorry. Like if I put this robot here, if I press play, you see I have a very, very nice user interface. This is nice, right? So you will learn how to do these kind of things where you can. So this is one of the stuff you will learn in this tutorial, like very simple one, just one slide, and etc. etc. So this is one nice robot. Then this is a tutorial to learn how to build robots. Like that will be your next week assignment with a great grade. Yeah. There is a robot here that it does the robot you have in here. We don't have it it's not implemented in VREP yet. So you go on the internet, you take the part number of the robot, Mitsubishi, whatever it is. You download, you try to find the CAD files. If not, you have to measure and make everything. you take the CAD file and then you follow this tutorial. And you will be able to import the CAD file and modelize everything and build the robot, and then you can add it to your own library, bibliothèque on Power. And you will learn how you will be able to do this stuff. Then you have the line following. This is a nice one too. It's a tutorial that will make you follow the line, some trajectory based on a sensor. You have a sensor looking on the ground. You have two sensors detecting white and black. Yeah. So when the robot is going to detecting some black part on the side, it will go on it will turn a little bit on the left until this sensor is detecting some black. So you will follow. You will oscillate if you have a line. Like you will, oh, I detect a line. Okay. Oh, I detect a line. I keep the line in between the sensor, and so you will follow you will be able to follow the line. This is something really nice in robotics. Invert kinematics is to be able to do this kind of robot where you select, you can actually even grab the target and take the robot by the hand. Example tutorial is, what is it? Ah yeah, you import some shapes. You import some shapes from the CAD and you make a mobile robot, etc. etc. And you have several stuff. And maybe this one is something you like to know how to do. So that after you modelize the manipulator, you will be able to modelize also the full, the cell. And then there are like other ways, but you will need to re-invite me to Costa Rica for more advanced stuff where you can actually do the kind of videos that I showed you at the beginning with very high level. You need to masterize a little bit there, but to be able to do that. But the learning curve is very steep, meaning that you start very, very quickly. You are able to, I promise you, you will be very quickly be able to do like this kind of crazy things like I showed in the presentation. Like, where is it? Like this famous video here. You will be able to do this kind of things. Like, but that's very advanced. But still, you will be able to simulate all these kind of things. So if you dedicate yourself a little bit with VREP, doing this kind of things means that you will be able to modelize this kind of a cell, production cell, and that might be very interesting for your future as an engineer to be able to say to your future boss, oh, what about doing this way for the production? We need to use this robot, and this. And instead of buying the robots and installing everything and to convince your boss, you modelize it in the rep, you do some tests, and you can program everything, and then you buy the hardware, you install it like in the simulation, and then you can make some extra code to be able to have a visualization, monitoring of the real thing. And prior to buy, you will be able to do some proper decision. So this is a very powerful tool for industrial engineering. Any questions? Pamela?
So, actually, I guess you're going to be here with us several times in the future, you know?
Yeah. That's why I went very slowly. so that I can come back for more.
That's a problem, don't worry.
Thank you very much.
No, muchas gracias a Eric, tal vez un aplauso, ¿verdad? Tenemos que comer, aquí podríamos quedarnos mucho tiempo, pero bueno, vamos a almorzar y bueno, tenemos ahí ese punto. Sí, así que, bueno, nuestro grupo entrará ahora después.